right, we'll just get started. Cool. Alright, so who here thinks they know what machine learning is? I'm sure you guys, yeah, what is it?
It's not like machine learning where you're learning how to make the machine learn.
Okay, learning how to make the machine learn. Jacob?
It's the machine learning how to make you know how to operate. Like, so it's like learning artificial intelligence. So like Google search algorithms that help you that like see what you're into and then suggest things based on that.
Alright, Tosa?
Teacher machines learn independently.
Okay, that's actually a pretty good explanation. Anybody else? Lady?
Extrapolating from a given set of inputs and outputs.
Does everyone here know what extrapolate means? Cool, yeah. Basically, like this, you're kind of making decisions based off trends of data. But yeah, those are all pretty good explanations. The way I would classify it is kind of like learning algorithms and using statistics for computers to complete a task. Whether that task is like pretty simple tasks like, oh, is this like black, is this white, or even making it move like a robot, like how a robot could actually physically decide to move. But the thing that's important about machine learning is its instructions are not very specific, right? So like an example of kind of losing this kind of specificity is kind of like a baby, right? Like if you had a baby, right, and you were this programmer and you wanted to teach this baby how to walk, like what would be like, it'd be so hard for you to tell the baby how to move each of its exact like feet, especially for per baby, right? You couldn't make a general thing. Like it's very general to take an Arduino, like the way we've had it, and make its a motor turn in one direction versus the other. You can do, it's pretty simple to change from one motor to another, or change from one Arduino to another. But like how to change like a baby, right? Like how would you teach a baby how to walk without learning every exact thing about a baby, right? Like it'd be, which one do you think would be easier to do? For the baby to learn by itself, or for you to learn everything about the baby to then teach it how to walk explicitly? Which one do you guys think would take longer?
To learn everything about the baby.
Yeah, to learn everything about the baby would take. There are people studying that right now, and I can tell you right now, people have devoted 30 years of research of their entire lives to try to think about how we walk, and they still can't do it. They still cannot figure it out to this day. So this is why we use machine learning, right? It's for things that we can't really understand that well, like directly, but we know it happens out there, right? Like when you look at a car, that's a car on the road, right? But it's be really hard for you to tell the computer every single thing about every single car for you to know like, hey, that's a car, right? So where it becomes really useful is there's a lot of data for things, right? Like we have spent a lot of time looking at cars. We spent a lot of time looking at clouds. There are millions of them. So it'd be easier for you to just, imagine if the computer could just learn by looking at a bunch of clouds that this is a cloud versus you telling everything about a cloud. Like here's a model for the human body. Like imagine you trying to sit down and code the movement of the human body versus like watching a lot of humans move and then just kind of figuring out how that works. That's what we do, right? Like you didn't learn immediately how to catch a ball. You kind of just felt your way through it and then learned how to throw a ball well, right? That's really how it works. Okay, so what are other examples of things that like you have a lot of data, but it'd be really hard to learn every single thing about this thing? Lady?
Driving.
Driving, yeah, autonomous driving. That's pretty hot right now, right? Who hasn't heard the phrase autonomous driving? Right, literally everyone. All right, what's another example? There's no other example where you think, yeah?
Playing a game, Aton.
What?
Aton.
Aton?
Like playing a game, you're not going to be told like in every situation what to do. You kind of just learn.
Yeah, playing a game. That's actually a really good one. Like chess, right? Like chess is a simple game, right? Like I mean, you're really only like 4 rules maybe, like in terms of movement, and then maybe like other things on top of that. But imagine if you could just teach a computer. A computer could watch a million games and then figure out the strategy versus like literally trying to code every single idea of strategy.
What about like Rubik's Cube solving?
Rubik's Cube solving? I think it actually has a pretty set algorithm at this point.
Oh, it does?
I think it does, yeah. Like I think you can like teach yourself within like 7 steps or something. I'm sure they're not easy, right? But I'm sure a computer could do it even quicker than a human. Cool. So one place where it becomes group machine learning has been really big lately is in image recognition versus classification. So here, like on the left, or your right, you're seeing these cars being like segmented into two different parts, right? So it knows it's a car. It's learned that this is a car moving, even while it's happening on the highway. And then on the left, you can see that like it knows not only that it's a bird, cat, or dog, but what kind of bird, what kind of cat, and what kind of dog, which is something we can do instinctively, right? But imagine coding all the different like rules for a computer to do that, right? That's why it's much easier for you to take, imagine millions and millions and millions of pictures of different cats, different birds, different dogs, and this is much easier to do than all the nuances behind it. So I'm going to go through like just a really quick example, right? So here are 3 different types of flowers that are all really similar. They're all in the same family, the iris family. And let's think about ways like what are some ideas of ways that you could differentiate the 3 of these flowers? Anthony?
Color and petal shape.
Say it again.
Color and petal shape.
Color and petal shape. That's a good one. Yeah.
Like structures.
What?
Like structures, like the petal with the leaves.
Yeah. Structures. Yeah. You and Beck. You have one. Okay. Anyone else? Any other ways to differentiate flowers?
The background.
Background? Background's possible, but I mean, they can be similar, but yeah, that's a good idea too. No one, nothing else? Yeah, you?
If they're different seed shapes and stuff.
Different seed shape? Yeah, that's a good idea. Definitely, yeah, that's good. So we're going to focus on 2 different, these are something in machine learning called features. These are things that we want to extract from an image or from any kind of thing that any data, things that we want that are differentiating, right? So the 2 features we'll be focusing, well, 4 features we'll be focusing on today are the petal and the sepal. So the petal is the part where the seed comes, and the sepal is kind of like the leaf. I don't know, I'm not a plant person, but these are just 2 things of a plant that are different. Anyways, so there's like the petal length and the width, and then the sepal length and the sepal width. So if we knew these 4 things, yeah. So if we knew these 4 things, what could we do? What do you guys think? Yeah, Costa, what do you think?
Collect data from many different plants, then label it, and then train the.
Label it? What do you think it would look like?
Like for each species,
Mhm.
in the family, you could input the data and then label that as that species, and then do that for all 3. A bunch of time and train the.
Yeah, so that's actually a really good vocab word to think about. Labeling. Right? If we knew each thing was an iris, what were the 3? Iris setosa, iris virginica, iris versicolor, right? We should label. If we know what this is already, let's tell the computer that this is that, and then kind of see if the data figures itself out. Is there any way that you think the data would look like? It'd be easy way to separate? Yeah, you?
Maybe the ratio of the petals of sepal.
That's a good one. I didn't think about that. The ratio, yeah. Even what about simpler? Yeah.
Like for the petals, like say like you have like a certain amount of like millimeters, like centimeters. And I guess you give like a range based on like how much of like a study you've done on like all of those kind of flowers. And like you say, alright, so like this kind of flower would fall between these ranges for like a petal, and then a sepal would fall between these ranges of like size.
Yeah, ranges especially. Yeah, that's actually like kind of close to what you'll see. So here's all the data. Here's all of it. Right, here's all the petal lengths, petal widths, sepal lengths, sepal widths. And then they're based on color, the 3 types. What can we do here? How could we separate any of them? Yeah, Costa? Can we do someone other than Costa? I'm about to call on someone, so anyone. So someone raise your hand. No? No one? Alright, you in the hat, what's your name?
Max.
Max?
Yeah,
Max.
well, clearly the green is almost always.
Clearly?
Yeah.
Why don't you raise your hand?
I don't.
Clearly? It's clearly? Tell me what's so clear.
I mean, in most of the graphs,
Yeah.
except for maybe 5 of them, the green is almost always separate from the red and blue.
Show me. Bring it up to your crowd.
Draw on the smart board with the expo marker.
No. I'm sure they're easy graphs to redo.
Yeah, okay. To redo, like
Yeah.
to draw.
Yeah.
So just that one, that
Which
one.
one?
This one. None of the dot graphs. All the green are separate from the.
I mean, kind of. What about this one?
Almost always, mostly separate. See, like, yeah, they're separate. Almost every place.
Okay.
So you can see that the iris setosa or whatever is it's different.
Or dry. What if you had to make a computer do it?
To make the computer do it,
Yeah.
like with these graphs.
Yeah, with any of them. Choose one. Choose your favorite.
Favorite. Let's do this one.
Okay. What would you do?
Like if I were the computer.
Yeah, if you were the computer.
If I were the computer, I would find each data point.
Mm-hmm.
I would see where they overlap, and those would be like the features where they overlap.
Mm-hmm.
And then because I have where they overlap, all I would do is some color recognition after I figure out where they overlap. Because this one will overlap, so clearly from that range, that's that type of flower.
Mhm.
But these do overlap very slightly here. So everywhere else, it'd be clear that they weren't the other flower. But in the overlap range, you would have to do a little bit of differentiating.
Okay. It's actually pretty good. So like, actually this is something called it's a pretty fancy name for it. But what he basically just described was a support vector machine. So, let me see if I have it. Yeah, here, yeah, this is it. This is it. Let's use, everyone knows what the linear equation is, right?
Yeah.
Y equals mx plus b. Super easy to remember. And this is basically what the computer does. Right here, in this one, we could just draw a line, right? We could just draw a line right here. If the line value is somewhere over here, then it's not this green one, the setosa, right? It's not the setosa. But if it's above that line, then it's one of the other two, right? That's basically what you said.
Yeah.
And you could draw another line through here, boom, and that's the third type. That's yeah, Costa?
Like make boundaries for each of the groups? on the
Yes,
graph?
exactly.
Do they always have to be linear, or can you make them more abstract?
That's a good question. I'll be referring to that later. But for this, right, we could just use a linear boundary, right? And so we can take this right here, this little equation. Right, we have a bunch over here. We label these, I don't know, I, V for that weather for the first one, and then we label these IS for the other iris, right? The other iris type. And then once we have, and then if we have a new, we use all these data points to train it, to train this line, because this line could be a little bit lower, right? It could be a little bit higher. But then once we have enough data, let's say we have millions of flower images, it'd be so easy to just plot it and know, boom. Anytime we get a new flower, it's probably gonna be this, right? And then like you said with the boundaries here, we kind of see that if we do use this label, use this line, notice this green one would be mislabeled, right?
Yeah.
This green one falls within the maroon territory. You see what I'm saying? So there is some, there always is going to be some classification error with things that are so close, like flowers. But think about how amazing it is that we can take a camera and immediately know exactly what flower that is. Where would that be useful?
Maybe for like just people who are casually walking through the forest and they're curious.
Mm-hmm. Okay.
About the plant type.
Yeah, Matthew?
I was thinking more along the lines of like endangered flowers.
Mm-hmm.
Like we cut down a lot of forests and stuff, so maybe like scan the place, see if there's anything endangered, take it out, then you can cut down your forest for
That'd be awesome to figure out the biodiversity, especially in like forests where like things are dying out, right? Imagine if like instead of having one expert have to go through like one world expert that gets paid a few $100,000, he has to go through the entire forest. Imagine if we could have people that we paid. No, imagine we could have robots that don't cost any money. We put a camera on them, they go through the forest, and we know everything about every species in that forest automatically. That sounds pretty lit, man.
I mean, for the people that, some people might lose jobs, but,
Who wants to go in the forest for days and days and days and days and days without food or water? Anybody?
$1,000.
That's the job. What I say?
For a couple $1,000.
you know,
We
you
do
probably
not
not
want
you
food.
could
We
do
don't
something
have
else.
food and water.
You can do something else and go to sleep
There's
in your own
better
bed.
in life.
We're not going to talk about it right now, right? But yeah, there's more, right? There's more, like somebody said, what about lines when they don't work? Is that you?
Yeah.
Yeah, right. What about here? We have three things, right? It's not just separate lengths, separate width. We have multiple things here. What could you do? Yeah?
Big boxes.
Make
X,
boxes?
Y, X, Y, Z.
Yeah, but then you're kind of stuck in that box, right? What happens if we get a new data point?
So you can make any 3D shape.
Okay, a 3D shape, that's okay. But this is already, Costa?
Abstract shape.
An abstract shape? What's
Just
an
a blob.
A blob, alright. Anyone else? Joe?
You could set a range and do linear regression.
Kind of, but linear regression also implies a line, right?
Sure.
What else? So
You can make a projection based on previous data outside of a range you already have.
Yes, but you're not saying the word that I want to hear. But you're close, you're really close. Anthony? A 3D line. But what is a 3D line really?
A flat box.
Vector, flat box. You're so close, man. What else? You guys are so close. What?
A plane.
A plane, bro. That's it. You just put a plane. You put a plane. That's it. And this is now. That's why the name of this thing is called the decision hyperplane. Okay? A decision hyperplane. So even though like this, even though this is a line, we call it a decision hyperplane. Okay. Right now I'm giving you words that.
Based on.
So yeah, exactly. You decide based on this decision, and then these things called boundaries, which is like how wrong or right you are, right? Because here you're kind of like, because you're so tight, you're more wrong. You know what I mean? Yeah. Yeah. Bust out a plane, dude. Just bust. Yeah. What's up?
Is it hyper because you decide which feature it is? Which
I don't know why they call it that.
Is
Honestly.
there like a hyper variable or hyper feature or something?
Maybe. Possibly. I just know it's called a decision hyperplane. But yeah.
But yeah.
Okay, but yeah, there exists many other techniques other than lines. Where like here, a line would not like. Is there a line you could draw that would actually tell you which thing is green, which one is maroon? You couldn't, right? Like if you did a line like this, you said everything on this side is green, you'd be wrong, right? Every sign on this, everything's maroon, you'd be wrong, right? You'd have 50% accuracy no matter what you do. So a line is never going to be enough here. Say after you do a hyperbole, right? It's called hyperplane. It is cool. Okay, cool. What about another example? Here's something you could do. You could make some. You could also make something linear. So okay. So let's say you had just one feature. You have one feature, nothing else, and it looks like this. Right? And then here are all the circles. Here are all the X's. Here are all the circles. What could you do to separate these? Baby?
Parabola.
A parabola, yeah. You made it too easy, bro. Come on. Wait, so yeah. Anyone understanding what he's saying?
Yeah.
What you could do? Could you draw it for me? Draw it for me? Yeah. Well, this okay. Yes, you're right. You're right in the conceptual, but I'll show you like the. Yes, thank you. Everybody, clap. Thank you. But imagine this is like a feature. Let's call this feature x1. You can make up a new feature, right? You can make up a new feature, and let's just call it x2. Where x2 just equals x1 squared. Right? Because then if it's 0 here, then x still stays 0, right? But then you could keep making x go up. You see, and then everything else is and so here it's pretty easy. Like, where do you draw a line now to separate? Just the line. And so now this is now your new support vector. So here you were kind of right. But if you wanted to use a linear vector, this is all you would do. Cool. You guys are pretty smart, man. You guys are artists. You're better than some grad students. Alright, but then some things are too hard, right? Like, some things are too hard to put to a single number, right? Like, what thing do you take out of a swan that's numerical that you can automatically know this is a swan? Right?
White and
Yes, it's white, but like, it's white where? Like, if you have this picture, this isn't white.
anything
There's like a
orange
percentage of it
pink
is
is white.
Percentage of white, but
You
then
would
the
need-
wall would be a swan.
You would need more than one thing.
You would need more than one thing? Yeah, like, there's
Anything with an orange beak is
anything with orange,
You would need more than one thing.
What? Jack?
Could you use multiple parameters and then tie them together in a logic statement?
Yeah.
Yes, but how many? Where would you stop? Like, bro, that's it. Exactly as many as you need. Let's just,
That's
okay.
why you have your that.
But, hold on. But then it changes. Like, this is a swan, but this is also a swan. Right? This is also a swan. What do we do here? What's up? What can you do, Hunter?
Make new parameters.
Make new parameters. But when do we stop? And which ones? What are they? Right? We're all getting confused. It's like,
parameters
that-
for
let
every
the
single
machine
case
decide.
of
At that point,
existence
it
for a
becomes-
swan.
but then how much? You need every swan ever, right? Like,
Yes.
So what if it's just breaking?
yeah, exactly. Yeah, exactly. But so there's this technique that's basically, yeah, like you said, it's called a neural net. But then let's look now at Abraham Lincoln, right? We can take out features from Abraham Lincoln by like giving literally every single pixel a value, right? Because all images are really just pixel intensity values, right? It's just how bright it is and then how colored it is, right? And then we take each pixel and then we just stop kind of worrying about it. We literally take each pixel and then we do something with some amount of pixels so that we just extract a feature out. So this part is where it starts to get really abstract. It's like, imagine like we had something like a really simple algorithm would be something like this. Imagine if we had like just 4, something like this, and it's like -1, 1, 1, 1, right? And then we just do this, and imagine there's a bunch of other numbers, whatever, just imagine it for a second. We have 1, 1, 1. And what if we could do something to this that like, we just add up all of these, and we add this up, and what is that?
That's 2.
2, it's 2, right? We have 2, and because it's greater than 0, it just stays 2, right? This is now anything. And then we had another box, right? And it's like 0, 0, -1, 0, right? This is equal to -1, right? Or actually, no, I should do this a little bit better. I'll do this a little bit better. Let's do it like this. Let's do like this. Let's do 1. Dude, life is just math. Okay, and then we just take this first quadrant, right? Take this first one. This maps to 2, stays 2. This one adds up to 2, right?
Yeah,
2. This one adds up to 1.
2.
1.
1. No, 2.
No. This one?
2. 1.
Alright. It adds up to 1, guys. And then this one? -1. But then, if it's -1, we just keep it at 0. We never have a negative value. We just decide that. That's just one of the rules. So this would be an example. This would be an example of like where you take all these features that we have, all these pixels, right? Even imagine if we had 1,000,000 pixels, right? And now we just divided how many we have by like half, at least, right? This is 9 to 4, right? So it's just bringing it down so that we have less features to worry about, right? So like imagine like before where we had like the pet, yeah, what's up?
Combining features.
Yes, no, we're actually trying to extract features. We're trying to see like what's important from all this data that we have.
Like, if we have 2 features that are basically the same, is that what you're doing?
But the thing is, this isn't defined as a feature, they're just pixel values.
So you're saying take like a general like thing and
Literally, that's what happened here.
yeah.
So if you look at the Abraham Lincoln thing, right, we have all this data that like,
All these
you know, like
details.
maybe it's something, but like this is a lot. We don't need this much, and then we just kind of threw a bunch away, right? We made it so it's less sharp. So we have value. This is easier to work with than this. You see what I'm saying? What's up, Costa?
So you're making it simpler, that means the quality of the predictions may lower.
Yeah, so that's nuance, right? That's something you learn. That's where the engineering comes in. Is like, at what point do we take away data such that it becomes in data that's important? You see what I'm saying?
Yeah.
That's where the engineering comes in. So that's where we kind of decide, like, all right, what do we do with all this data such that we get to a place that it's like good enough? You see what I'm saying? And that's where you do a bunch of testing and tuning. That's really where it comes in.
Trial and error.
Yeah, so this is like the idea here, right? It's like, let's imagine we take all this data from our pictures and then we just mess with it. Like, we could do something like that, but then the computer learns to figure out which way is the best. Like, the algorithm I use where like if it's negative, it's a 0, I just decided that. But the computer then decides, by the fact that we have these labels, right, we know what's right. We know which ones are right and we know which ones are wrong, right? And then we tell the computer to mess with this until we always are basically always right. Matthew?
Isn't that why like we can't just do this one time and that's it? Like you have to make like generations of
Yeah,
like,
training to make the computer learn to do something like this, to make the computer learn that like this is the best algorithm to do here,
it's like
can take
survival
hours.
kits.
It takes hours. It has to take a long time. That's why we have supercomputers. There's some supercomputers that run just off environmental data. That's why the meteorologist is like, this is probably the weather's going to be tomorrow. That's because we have literally thousands of days, thousands of contexts to choose from. So, I'll tell you one fun example of this stuff. Alright, cool. So since you volunteered so much, come on. Come here. Hurry, with the quickness. We have to finish up soon. Draw a number, Costa. Draw a number.
Like drawing?
7. There it is. So guess 6, and 5 and 2. Draw another one. Draw it really badly. Really badly.
Draw like a 7 with the dash.
What was that?
Is that fire?
That's a 2. That's a 2? Hey, guess 2! Dude, try really bad. Really, really bad. Really bad.
Do like a scribble.
You draw scribble.
What?
Yes.
Alright, that one was too bad.
It looks like
I'm gonna try 7.
That's a, see, yeah, that's a good 7.
That's a good 7?
Yeah, I could tell.
line.
But yeah, guys,
Yeah,
basically what it does, it
draw
literally just, look here, look at what it's doing. It's taking these values at the edges and then bringing them to like just one single value, right? Until eventually it keeps taking whatever data it has here and fitting it the best it can to a value that it already has. It can only do 0 to 9, so it knows it has to be one of those, and then kind of just minimizes the errors. But yeah, that's basically it. That was my discussion.
Did you make that?
This one? No, I wish. I Any questions?
Any questions or anything?
They asked funny.
First guess.
No questions?
Last question? Alright. Morning, students. Thank you so much.